Today we're going to talk about the dimension of a vector space. To this end, let's first review the basis of a vector space. We start out with the result that will help us to determine when a set S is a linearly dependent set. Let's say that T is a subset of a vector space V, which is linearly independent. We'll choose a vector lowercase v not in T, and then consider S to be the set that we get by joining this vector lowercase v to T. Then lowercase v is in the span of T if and only if S is a linearly dependent set. We'll come back and we'll use this idea a little bit later when we work out some proofs. Next, given a subset beta of a vector space V, the following two are equivalent. First, beta spans V, and beta is a linearly independent set. Second, every vector, lowercase v, in our vector space V can be uniquely expressed as a linear combination of vectors from beta. If either of these two properties are true, we'll say that beta is a basis for V. Last time we found lots of examples of bases. If V is the trivial vector space, then the empty set is a basis for V. Let's consider the case where V is R2, namely the real plane. Given any two real numbers A and B not zero, we can define the vectors U1 and U2 that you see here on your screen. Beta, the set containing U1 and U2, is a basis for R2. In particular, when A equals 1 and B equals 0, we recover vectors that we denote by E1 and E2. They form what we call the standard basis for R2. Similarly, let's consider V to be R3, 3 space. Given any three real numbers A, B, and C such that A and B are not both 0, we'll denote U1, U2, and U3 as vectors that you see here on your screen. The set containing these three, beta, is a basis for R3. When A is 1, B is 0, and C is 0, we call the set containing them, namely E1, E2, and E3, the standard basis for R3. More generally, let's consider the collection of M by N matrices over a field F. Then we can express every vector as a linear combination of these matrices that we denote by E superscript ij. The collection of these matrices is what we call the standard basis for this collection of matrices. Now, we can introduce the concept of dimension. And we'll begin with the result that explains how. Let's let V be a vector space and say that V is spanned by some finite set S. First, every finite basis V has a finite basis beta contained in S. And second, every basis beta of V has the same number of elements. Well, if we have a basis, then we count the number of vectors in that basis. That's what we call the dimension. So again, the dimension of a vector space is the number of elements in a basis. It doesn't matter which basis you choose because every basis of V has the same number of elements. We're going to spend some time proving these two statements, and we'll prove the first one by induction on the number of elements in S. That is, let's consider the following proposition, P of n, for a non-negative integer n. If V is spanned by a subset S containing n vectors, then there exists a linearly independent set beta contained in S that also spans V. The way to think of this is as follows. We can start with an S that spans V, but S may not be a linearly independent set. The idea is that we'll want to remove the quote-unquote bad vectors from S until we whittle down to a set beta that is linearly independent and hence a basis. This will be how the proof will go. You'll see that we can start to remove the vectors one by one until we arrive at what we want. Let's focus on the case when n is equal to 0. That is, let's say that we have a set S that has no elements. In this case, S will be the empty set, and the span of the empty set we know is the trivial vector space. Since we know the empty set is a linearly independent set, we see that proposition P of 0 is true. That is, that the zero vector space does indeed have a basis. Let's assume that proposition P of n0 is true for some non-negative integer n0. This will be our inductive hypothesis. We now want to consider the next case, namely n0 plus 1. So to this effect, let's say that V is a vector space spanned by a subset S that contains exactly n0 plus 1 elements. We're going to exhibit a basis beta contained in S. This means that we're going to consider two cases. First, let's say that S is a linearly independent set. Well, in this case, if we have a linearly independent set that spans V, we'll choose beta to equal to S. Then by definition, beta will be a basis for V. In the second case, let's say that S is not a linearly independent set. That is, it is linearly dependent. Let's write out the n0 plus 1 elements of S as u1, u2, u sub n0 plus 1. And let's say that we have a non-trivial expression for the zero vector. Since not all of the scalars a sub I are 0, without loss of generality, let's say that maybe the last one is not 0. That is a n0 plus 1. If this is the case, we can then solve for the last vector, a n0 plus 1, in terms of the first n0 vectors. So this actually means that n0 plus 1 is in the span of T, where T now just contains n0 plus 1 vectors. So this shows that V is the span of a subset containing n0 vectors. According to the inductive hypothesis, there now exists a basis beta for V contained in T, but of course T is contained in S. So this actually shows that proposition P n0 plus 1 is true, and hence the first part of the theorem must be true. Let's now focus on the second part of the theorem. Why is it that every basis has the same number of elements? Well, for the moment, let's say that we perhaps have two different bases for V. Beta contains n elements, and gamma contains m elements. If this is the case, then of course, since we know that the span of beta equals the span of gamma equals our vector space V, then we can express every element in beta as a linear combination of elements from gamma. Here's where you see u sub 1 we can write as b sub 1 1 times v1 plus b sub 2 1 times v2 plus b sub m1 times vm, and so on with the other u's. Similarly, gamma should be contained in the span of beta, so I can write v1 as a11 u1 plus a21 u2 plus an1 u sub n. So again, I can write every element, the u's from beta, as linear combination of elements from gamma, and I can write every element, namely the v's from gamma, as linear combination of elements from beta. Now, what you can do is you can take the expressions for the v's as linear combination of the u's and substitute those into the expressions where the u's were the linear combinations of the v's. And after you stare at things for a bit and realize that beta is a linearly independent set, then you see that m has to be n. There's just no other way around it. Another way to say this, as we get more advanced throughout the course, is that we actually do have a product of matrices. We find a couple of different identity matrices, and we'll find that our matrices have to have the same size. M has to be N. Now let's try to end today's lesson by going over some examples where we have actually computed what the dimensions are. Let's go back to the example of R2, namely the real plane. If A and B are not both 0, then recall that we can define these vectors u sub 1 and u sub 2 that form a basis for V. In fact, notice that because A and B are pretty much arbitrary, there are infinitely many bases for V. So it's not fair to say there is the basis, there could just be a basis. But in either case, even though there are infinitely many bases, there are just 2 elements in this basis. So if you pick any A and B that you'd like to form a basis beta, it doesn't matter because it'll always have exactly 2 elements. A similar thing happens for R3, for 3 space. We see here on the screen that there are infinitely many choices of a basis, beta, but it doesn't matter. In either of these choices, there's exactly 3 elements in this basis. So we would say that R3 has dimension 3. More generally, say that we have m-dimensional vectors. We've already seen an example of a standard basis for Fm, and our standard basis here, beta, has exactly m elements. So in particular, an m-dimensional vector space, this Fm, has dimension m, as the name suggests. This explains why we're using this notation F superscript m. The m really does suggest that we have dimension m. Next, let's consider the collection of m by n matrices. We've already seen an example of a basis for this. Our standard basis consists of these matrices E superscript ij. Well, because there are m rows and n columns, there are m times n number of matrices E superscript ij. In particular, the dimension of the space is m times n. Again, the notation here suggests what the dimension should be. Finally, let's consider the trivial vector space. Well, we've already seen that the empty set is a basis, and the empty set has no elements. So this means that the dimension of the trivial vector space is 0. Here we want to be careful that the dimension is not the number of elements in V. It has something to say with the number of elements in the basis. So even though V here, for the trivial vector space, has 1 element, a basis for V has no elements. Therefore, the dimension of V is 0. Thanks for listening.